so let's continue our application of the principles of quantum mechanics. Today we're going to extend our box into a two-dimensional system and 3 dimensions. So this time around we're going to have our particle confined into a rectangular box. Okay, so we're going to define the particle to be contained within a box that goes from x equals 0 right here to x equals, let's call that L1, and along the y-axis from y equals 0 to y equals L2. So it's within that box. So same thing as before, just like the one-dimensional problem, we're going to have, okay, it should be potential energy as a function of x and y. Okay, should be 0. It's constant. Okay, inside the box, that means there's no forces acting on the particle inside the box. So that's from x between 0 and L1 and y between 0 and L2. Okay, and then we say that psi is infinite outside the box. That means outside the box, potential energy is infinite outside the box. That means psi equals 0 outside the box. Okay. So what's our time-independent Schrodinger equation for the particle inside the box? What's the time-independent Schrodinger equation? H hat psi equals E psi. And what's the Hamiltonian operator? That's the kinetic energy operator plus potential energy operator. Call it out for me, James. What's the kinetic energy operator due to what's the operator for kinetic energy due to motion along the x-axis? Negative h bar squared over 2m second derivative with respect to, okay, and this time since we have 2 independent variables, we have to use partial derivatives. Okay, so partial derivative with respect to x plus kinetic energy due to motion along the y-axis, negative h bar squared over 2 times the mass times the second derivative with respect to y of psi gives you back E psi. So you have a 2-dimensional problem here. Your psi is going to be a function of two independent variables, x and y. So how do we solve this differential equation? Well, we're going to simplify our problem. We're only going to look for solutions that can be written as a function of x times a function of y. Okay, because we can, just like we did with time and coordinates, we can actually separate variables here. So we are only going to look for solutions where your wave function is a product of a function that depends only on x. And to make it easy to remember that that part depends only on x, we're going to use capital X to call that. We're going to call that function capital X. And so a function that depends only on x times a function that depends only on y. Okay, we can actually prove that there are solutions that are of this form. It doesn't mean that all solutions have to be of this form. All we're trying to say is if in this particular case we can do that because our Hamiltonian, okay, if you can show, if your operator is a sum of components, operators that affect different variables, then you can show that the eigenfunctions of that operator can be written as a product of functions that depend on the different variables individually. Okay, so if you go back to our Hamiltonian, you'll notice your Hamiltonian, okay, has a part that depends only on x and a part that depends only on y. So it's a sum of, you can think of it as a sum of 2 operators. An operator that affects only the x variable, an operator that affects only the y variable. And in that case, we say your variables are separable. You can write the eigenfunction as a product of something that depends only on x times something that depends only on y. And so let's go ahead and prove that.